We're told to set up an exponential equation where t equals 0 corresponds to 1970. And we're also told that the amount of carbon is about 325 parts per million in 1970. So that's going to be our A0, our initial amount, 325. And in 2020, we're told the amount is 413 parts per million. So that gives us one more data point to use. Since we know what A0 is, we can go ahead and start writing down our model. It's usually A equals A0 times 1 plus R to the T. A0 here is 325 because we're starting in 1970. So our model says A equals 325 times 1 plus R to the T. And to finish up the model, all you need to do is find R, the rate. We have one piece of information available to us to be able to solve for R, and that's the fact that when T is 50, A is 413. So that's what we'll plug in next to find R. So write down 413 for A. 413 equals 325 times 1 plus the rate, which we're trying to find, raised to the power of 50. Because when T is 50, the amount is 413. So now we just got to solve this equation for R. The first thing to do is to clean this up a little bit by dividing both sides by 325. And the reason you want to do that first is that if you do that, then you can easily just take the, raise each side to the power of 1 over 50. So you're really taking the 50th root of each side. It's easier to just write it as to the power of 1 over 50. And that equals 1 plus R now. So if you want to solve for R, just subtract 1 from both sides, and that's the rate. So when you go back to plug that into your model, you can just plug it in like that, but it really looks nicer if you get a decimal approximation. So I'm going to go ahead and get a decimal approximation. I used Wolfram Alpha to get my decimal approximation. It's a free online calculator, basically. It can do a lot of graphing and a lot of nice things. So I like to use that, WOLFRAM Alpha. But you can just use any calculator to calculate this. We get that R is 0.0048. That comes out to about 0.48%. And when you plug that back in, you get this nice looking model. If you're doing it by hand, you can't get a decimal approximation. That's okay, just leave the R in there. When you do 1 plus R, the 1 minus 1 will cancel each other out. So it won't look that bad. For part B, we're doing this exact same problem, but we're just setting up the model a little differently. We're using the number E, which is pretty popular. It's pretty convenient to use when you're analyzing these models with calculus. So when we do this, 325 is still the initial amount. We're still going to use the fact that at T equals 50, the amount is 413. But this time, instead of solving for R, we're solving for K. So clean it up by dividing by 325. Then you can rewrite this in exponential form. You can do that directly, or you can take the natural log of both sides. When you take the natural log of e to the 50k, you just get 50k. Divide both sides by 50, and that gives you k. And if you want to, you can rewrite that. You can rewrite k with the 1 over 50 up in the exponent. If you do it that way, you can write your final answer in a little bit more simple format. Remember, there's the logarithm property that says you can bring a multiple in front of a logarithm up as an exponent on the stuff in parentheses. I calculated this number with Wolfram alpha as well, and I got 0.00479. Notice that's really close to what we got for R. We got 0.0048 there, 0.00479. So super close. There's a very deep reason for that. Well, kind of deep reason for that. You can show why they're very close using calculus. And what I'll tell you is that the smaller R is, the closer K will be to R. If you let R get bigger, like 10%, 20%, 30%, then the K will be a little bit more off from R. But here they're almost exactly the same. So we just go back and plug in that number for K in the model.